Hello, everyone. Thanks for joining. I'm Rouditchenko, PhD student in MIT CSAIL in Spoken Language Systems Group, working with Dr. Jim Glass and a couple other people here. So thanks for joining. Today, I'll be presenting my talk called Giving Sight to Speech Models. So in recent years, we've seen major advances in speech recognition models where the models are able to take audio as input and they're able to transcribe speech, meaning given audio, to output text in the same language, but also to translate speech, meaning given audio, outputting text in the different language. One such model is OpenAI's Whisper, and Whisper was trained on around 700,000 hours of audio data in different languages, and it's able to transcribe speech and translate. However, Whisper and many other models have a problem. Their performance decreases in noise. So shown on the right here on this plot is the performance of Whisper and many other speech recognition models when we vary the signal to noise ratio of the noise. So we can see as the noise increases, meaning the SNR becomes lower here, when the word error rate is getting higher, and higher word error rate means worse. So this is a problem we'd like to solve because when we deploy speech recognition models, you never know the type of background sounds you might encounter. Audio-visual speech recognition is a classic methodology to try to boost the performance and noise. And AV speech recognition combines the lip-based video with the audio. And audio-visual models can be 2 to 3 times better than the audio-only models in moderate noise, for example, 0 signal-to-noise ratio. However, there's a general problem that audio data is much more abundant than video. And because of this, the foundation models for these respective tasks have a huge discrepancy in the amount of training data. For example, Whisper, again, was trained on 680,000 hours of audio training data, while AV Hubert, a state-of-the-art lip reading model, was trained on 1.7 thousand hours of video data. So in this work, we ask, how do we improve the audio-visual models with a limited amount of video training data? So this leads us into the first work called Whisper-Flamingo, integrating visual features into Whisper for audio-visual speech recognition and translation. And this was done with the following authors and presented at InterSpeech 2024. So the goal of this work is to combine those pre-trained audio speech recognition model, Whisper, with the visual speech recognition model, AV Hubert, for the AVSR. And in particular, we want to use Whisper's strong multilingual capabilities, first for English speech recognition and also English to X speech translation, where we have English audio as input and multilingual text as output. So first I'll describe the method. We have 2 stages of training, and in the first stage, the goal is to make Whisper more noise robust. So in this stage, we fine-tune the audio-only Whisper while adding noise to the audio. And this noise includes speech, music, and babble. And in this part of the training, we're fine-tuning all of the parameters of the model. For stage 2, this is where we start to inject the visual features into Whisper. And just to remind you, Whisper has never seen visual information. So we kind of have to be careful in the design so that the model can effectively integrate the new modality. So in this stage, we freeze the audio-only Whisper that we fine-tune, and we add the new trainable cross-attention layers into Whisper's decoder. And these cross-attention layers allow the model to attend to the visual features. And in this part of training, we train it on the audio-visual inputs. So the way that we propose to integrate the visual information is inspired by DeepMind's Flamingo. So with DeepMind Flamingo, they integrated visual features into the text language model using gated cross-attention. I believe it was one of the first mainstream vision language models. So inspired by this, we use the gated cross-attention to inject the visual features from the AV Hubert model into Whisper's decoder. And the equations for the gated cross-attention are shown below. And these are initialized as the identity function. And that's specifically because the alphas are initialized to 0, and you get tan h of 0 equals 0. So the attention part is canceled out, and you're left with the identity in the beginning. So that means that the model isn't attending to the visual features at first. It slowly learns to attend to those features, and that makes the training more smooth. We also enable a new task for Whisper. So previously, it didn't have the task of English to X speech translation. It only did the inverse direction, which was given multilingual audio going into English. But it was pretty straightforward to enable this for the model by training it on English audio. And we paired that with translations in 6 different languages. And these are the supported languages. So this is a schematic of the model. And so this part in the middle should look familiar. We start off with the Whisper audio transformer, encoder, and decoder. Then we have the AV Hubert video encoder, which takes in lip-based video where the video is cropped on a person speaking. And this model extracts representations which are then fed as input into Whisper's decoder. And in Whisper's decoder, we are adding these new gated cross-attention layers where they're attending to the visual features. So you can see that this diagram depicts stage 2, where we essentially freeze all of the model, insert these new gated cross-attention layers, and train them in order to attend to the visual features. And finally, to enable the English text translation, we have the standard next token prediction. For the experiments, we use a data set called Mavic, and it has 433 hours of English video for training, 1 hour for validation, and 1 hour for testing. For the models, we have the 3 largest sizes of Whisper. And when we add our AV Hubert encoder and the gated cross-attention, we can see that we scale up the model size, and the largest model becomes 2.5 billion parameters. And for the metrics, we have word error rate for English transcription and blue score for English text translation. For the testing scenario, we first test the model on the clean audio. That means without adding noise. And then we add noise to the original audio. And for the first results I'll show you, it's babble noise. So there's 30 different speakers talking at the same time. And it's added at a signal to noise ratio of 0, which is pretty hard to hear the person speaking. And note that we only add noise to the audio, not the video. So here's the results for English transcription. So first off, we have Whisper without any fine tuning. This is just the 0-shot model that you can download and test yourself. So first of all, the clean performance is pretty good, 2.1. It's pretty respectable. However, when you add a moderate level of noise to audio, it gets significantly worse, and it goes up to 20.8. We fine-tune the model in noise, and that helps the noisy performance a lot. It goes from 20.8 to 11.7. And as a nice benefit of fine-tuning on this kind of in-domain data set, we also get benefit on the clean word error rate from 2.1 to 1.1. This is the main result, that audio-visual Whisper-Flamingo performs the best in noise. It's going from 11.7 to 5.6. And we also maintain the clean performance. And compared to the kind of one of the previous R methods, we're able to get better clean performance and slightly better noisy performance as well. So how about other noise types and noise levels? Because I just showed you one particular type of noise. Well, we evaluated on 6 different types of noise. So 3 different babble settings constructed from different sets of speakers. We also have the side speech, which is just a single speaker talking at the same time, music, and natural noise. And in this setting, we averaged the results over 5 different signal to noise ratios, where -10 would be the most intense, basically impossible to hear the person speaking, and 10 would be pretty light noise, fairly easy to hear the person speaking. So here we can see for each different noise type, we've averaged the results over the 5 different SNR levels. And first off, we have the Whisper 0-shot model in red. You can see that it has the highest word error rates, which is bad. And when we fine tune the model, we can get a boost in all of the noise types, especially side speech improves a lot from 41.3 to 20.1. And finally, we have Whisper-Flamingo in the green. It's doing the best out of all 3 models. It shows that the visual contribution definitely helps in all the different types of noise and the different noise levels. I'd also like to compare to a recent AVSR model called Llama AVSR from Meta. So they propose to take a LLM, Llama 3.1, 8 billion, and similarly to use the audio and visual encoders from Whisper and AV Hubert. And instead of using Whisper as a decoder, they use Llama as a decoder. comparing the total parameters, our model is much more lightweight because our decoder is much smaller, and their model is almost over 3 times larger than ours. In the clean scenario where we don't have any noise, we essentially match the performance with 433 hours of data. And with if we scale up the data to almost 2,000 hours of data, we're basically in the same ballpark as theirs. So I'd like to point out that our model can essentially achieve pretty good results and match Llama AVSR, despite being a much smaller model. Finally, these are the results for English text translation. We have blue score where higher is better. And these are the average scores over 6 languages. So first of all, we have, again, a Whisper audio only model with the, in the clean performance, it gets an average blue score of 22.7. Now we have higher is better. And then when we have the noisy data, the performance decreases significantly to 18.6. However, our audio-visual Whisper-Flamingo is able to get a noticeable boost in the noisy performance from 18.6 to 20.5. And also the clean performance is maintained. And finally, compared to the previous state of the art, we get better clean performance and slightly worse noisy. However, the previous state of the art, they fine-tune separately for each language. So they have a model for English to French, English to Portuguese, etc. Versus our model was just trained once on all the different language pairs. And this could be a more scalable approach for, say, if we wanted to train on 100 languages, for example. Okay, so now this is the fun part. I'd like to show you a demo video. Let's see.
It's using past experience based on similar situations to try to make meaning. It's using past experience based on similar situations to try to make meaning.
Yep. So given that, given that heavy noise, our model was still able to predict most of the words correct. And in fact, it only got one word incorrect in the noisy audio. Okay, great. So far in this presentation, I've shown you kind of the model, which takes only English videos as input. So now I'm going to show you the extension of the model, which goes from English to multilingual video inputs. So far, if you've noticed, our model only used English video inputs. We use Whisper's multilingual text decoder for English text translation, but we haven't used Whisper's multilingual audio encoder yet. However, Whisper was trained on audio in 100 languages. So we were wondering, can we train a multilingual version of Whisper-Flamingo on videos in different languages? To develop the model, we continue to work with the Mavic dataset, which has videos in 9 languages. And the goal of this model is that the AV performance should be better in noisy conditions than the audio-only model for all languages. However, when we applied the default training setup from Whisper-Flamingo, it worked well for English, but it didn't work well for the other non-English languages. So our solution is to introduce a decoder modality dropout, which is key for this good multilingual AVSR performance. In modality dropout, the input modalities are randomly dropped during training. And the point of this is to better capture the cross-modality correlations while preserving the unique contributions of specific modalities. And modality dropout has been used in AVSR models previously to prevent the models from over-relying on the audio modality. However, most of these methods used early fusion, while ours uses late fusion. Early fusion was used a lot by previous state-of-the-art models, and how they work is that they have a single transformer encoder, which is designed to sort of process and fuse both of the modalities. The way it works is that each modality is processed by a lightweight encoder that's not a transformer, and then these features are combined usually through addition or concatenation and fed into the transformer for the kind of the fusion part of it. And during training, one of these would be randomly dropped. And this audiovisual encoder is supposed to handle this incomplete stream. Meanwhile, our method employs late fusion, where we have each modality processed by a separate audio and visual transformer encoder, and our decoder has separate cross-attention layers. So we use decoder modality dropout, where we randomly replace the inputs in the decoder's audio and visual cross-attention layers with zero vectors. And this operation, cross attention with the zero vector, results in a zero vector, but the output from the cross attention block would incorporate the bias and the linear transformations. So the point of this is that now the decoder handles the incomplete input stream, and the encoders can stay specialized on their specific modalities, while the decoder learns the better multimodal integration. And as for the probabilities of using audio-visual, audio-only, and video-only inputs, we define them as PAV, PA, and PV. This is the new schematic for the mWhisper-Flamingo model. On the left, this is essentially the same as the previous Whisper-Flamingo model. Now we can see that there's a PAV corresponding to the probability that we use both audio and visual features. And we have the cross attention going to both video and audio. Meanwhile, for the video only and the audio only, we now have cross attention going just to one of them, and the other cross attention is replaced by a zero vector. In our experiments, we found that the best combination was 50% audio visual and 50% video only. And I'll show an ablation on this later on. For the experiments, we continue with the same data set, except now we're using all 9 languages, and that's around 1.1 thousand hours of videos. For the models, for the mWhisper-Flamingo, we mainly build upon the small and the medium size models, and we're still using the word error rate for transcription. These are the languages of videos in Mavic, and you can see that English has the most amount of data. There's 4 languages with above 100 hours of data, and then 4 languages with less than 100 hours of data. And on these languages, we're usually seeing much worse performance, and that's obvious because it's harder to learn a better model on this less amount of data. And finally, some other differences to the previous Whisper-Flamingo. So first of all, the previous English model just used AV Huber trained on English videos, but now Whisper-Flamingo, the new version is using one pre-trained on multilingual videos. And in stage 2, if you remember, that's when we train on audio-visual inputs. Here, we're fine-tuning the visual encoder, which is, and previously it was kept frozen. Okay, so this plot shows the performance in the clean scenario without noise, comparing on every one of the 9 languages in the data set. And we're comparing the previous state of the art, XLAVSR, 2 billion, versus our mWhisper-Flamingo medium, 1.4 billion in yellow. You can see that across the 9 different languages, we're doing better on, I believe, every single language. And in particular, for the languages with less amount of data, we're seeing a much bigger improvement, and we can attribute that to Whisper's extensive pre-training on those languages. Okay, now I'll show the noisy evaluation, where again, basically follows the previous noisy setup I showed you, except here, we're specifically focusing on the audio evaluation on non-English languages, because that's the point of this work, to try to improve the performance, not on English, but on other languages. So we focus here on Spanish, French, Italian, Portuguese, and we have 5 signal-to-noise ratios. So here, for every noise type, we're now evaluating on 4 different languages, 5 different SNRs, then we average across all of them. So again, in the red, we have Whisper Zero Shot, which is performing basically the worst out of all the models. And we have Whisper Fine-Tuned Noise. It's doing better because the bars go down. And finally, mWhisper-Flamingo is doing the best. We see that the bars are the lowest. And when we scale from the small to the medium model, we can see across the board, the word error rates are better. So first of all, scaling the model size improves the performance, but we're also seeing the same trend that mWhisper-Flamingo performs the best, confirming the advantage of the visuals. Okay, so now I'm going to play the video.
Cuando tenía 5 años y empezaba a leer, mi querido abuelo Carlos Felipe me regaló un libro de aventuras.
Et pourtant, les scientifiques des Nations Unies prédisent un effondrement des pêcheries d'ici 2048.
Le donne fanno, con qualche importante e luminosa eccezione, altre cose.
И единственный способ не жалеть в конце жизни – это поверить и прыгнуть.
If any child is found violating these rules, he is severely reprimanded.
Okay, so we could see that the model could predict most of the words, but there were definitely more mistakes. It shows that there's room for improvements with the multilingual model. Okay, finally, here's the ablation study regarding the decoder modality dropout probabilities. As I mentioned, the setting probability of audiovisual at 0.5 and probability of visual only at 0.5 work the best, where we're getting 36.6 across average across 4 different non-English languages. If we apply the default setting from the previous work, which was no dropout, we're getting 44.6, which is much worse. It shows that we need to have this modality dropout to get better non-English performance. So if we go from that scenario of no dropout and we start to add dropout, if we only add audio only inputs, meaning we drop the video, this actually doesn't help. The performance stays the same. And then it shows that it's important to have the video only inputs. So once we start mixing those different probabilities, we could see that using video only inputs without audio only inputs works the best. And finally, we arrive at the best setting. Great. So in conclusion, mWhisper-Flamingo and Whisper-Flamingo, they combine the strengths of Whisper, the audio model, and A.V. Hubert, the video model using gated cross attention inspired by Flamingo. And mWhisper-Flamingo obtains the new state of the art for multilingual AVSR on Mavic dataset in 9 languages. And audiovisual mWhisper-Flamingo is significantly outperforming the audio only Whisper model tested on noisy audio. And finally, this is a general framework and can work better with audio and better audio and video models in the future, not necessarily Whisper and A.V. Hubert, but potentially whatever in a few years the next state of the art is going to be. So all of the code models and the demos were released on GitHub. We're welcome to take a look. Any questions?
So for A.V. Hubert, it also is trained with audio input. So in your case, you get rid of that and just retain the video.
Yeah, we didn't use the audio input with A.V. Hubert, but I think it could be interesting to try to ensemble it further, like have an audio encoder going to Whisper, audio going to A.V. Hubert. Just for simplicity, since we're building off Whisper, we decided not to use audio with A.V. Hubert.
And I guess A.V. Hubert works with video only setup. That's why you freeze it in your model.
Right. Yeah, since they train it with modality dropout on audio and visual, then the model can work with the video only inputs as well.